So here we have to the north the Sahara Desert. The colors are the topography over the region, and south of the Saharan Desert, we have the Sahel region. Well, a number of the stations indicated there are operational sounding sites. And the next, please. There are two sounding networks that were set up there, some with additional sites added, but some using existing sites. And these form a basis for our study. And the next, there's a MIT Doppler radar was located at Niamey, which sampled these squall lines that move through the region. So that's the focus of the study. Look at these squall lines connected with these African easterly waves. Next. Whoa, okay. So that network, we developed a gridded data set from that, all those soundings, 1 degree by 1 degree gridded data set, 25 hectopascal vertical resolution, to study the characteristics of these disturbances that move through the region. So this is a time series here of the onset of the West African monsoon that goes from June 1st to the end of September, equator to 20 north. And these are averages of the daily trim rainfall and the 500 millibar vertical motion field between 0 and 7 east. So this encompasses the most dense area of soundings. And one can see we have a region, if you can click next, please. One can see that up through the month of June till the first week in July, most of the convection was confined to 5 north or south. But then after the first week in July, convection jumped northward for several months. And we call this first period the pre-monsoon, the second the monsoon period. So we'll look at both of those periods. Next. These are PPI images of two squall lines that moved through the region, one on 19 July and the other on 11 August. This is during the monsoon period. And most of the squall lines were of this nature, north-south oriented convective lines with a trailing stratiform region moving off to the west at an average speed of 17 meters per second. Squall line convective lines were narrow, of course, maybe 20 kilometers wide, but the stratiform regions were very extensive, several hundred kilometers. So the analyses that we carried out are able to sample the vertical motion field, divergence in vertical motion fields in the stratiform region, but not the convective line region. Next. So let's look at the changes following monsoon onset. If we, yeah, this is an earlier version of this one. And on the left panel here, we have the pre-monsoon period. And if you look on the lower, you can see the lower plot, you see the rainfall peaks just south of 5 north. But after the monsoon sets in, you see the rain shifts to the north. And in the upper panels in color are the apparent heat source and in color, and the vertical motion field in contours. And you can see that after the monsoon sets in, the heating ascends, the heat peaks ascends and strengthens and shifts to the north, consistent with the rainfall shifting to the north. Next. This two panels show the pre-monsoon and monsoon periods zonal wind and absolute vorticity. If you click on the next, there will be an arrow which pops up. It shows this African easterly jet around between 600 and 700 hectopascals. And then the next, after the monsoon sets in, this jet shifts to the north. And you can see in the color there that's the absolute vorticity field shown in color. And there's a reversal in the gradient of the absolute vorticity, which is a necessary condition for barotropic instability. These are now averages over a long period of time. So in the mean, then there's this reversal in the absolute vorticity gradient. Next slide, please. These plots show the potential vorticity field pre-monsoon and monsoon. So next, there should be an arrow there that shows the colors are the potential vorticity field, and there are also contours on those. We also put the rainfall in the lower panels. So prior to the monsoon, you can see there's a tongue of high PV that extends from 20 north southward to 5 to 10 north from mid-latitudes or the subtropics. This high PV is associated with the deep convective boundary layers over the Sahara that raise a lot of dust, and you get convective heating that there's an enhanced stability at the top of this deep adiabatic layer, which leads to these high values of PV, which are extrude into toward the tropics. Next arrow. And the PV field, if you look at the north-south gradient of this PV field, the stippling shows where there's reversals. And this goes back to where Bob Rupa shows that this indicates there's therefore possible barotropic baroclinic instability of the zonal flow in this region associated with the African easterly jet. Next. So what we've done is to take a composite of these squall lines following the monsoon onset, and we've used a work of Nieto Ferreira, who studied nearly 24 cases. And so we've created a composite of 12 cases here. And if we look at the lower axis, there's time relative to the passage. So time 0 is when the convective line passes. Negative times are before line passage, and positive times are positive values are times after passage. Basically, we can't sample the convective line structure, but we are sampling here the stratiform characteristics that are following the line passage. Next. So what you see here is the after the squall line moves by, you see warming aloft, and then also warming atop the boundary layer associated with a mesoscale downdraft in the stratiform region. Next. And this next one shows, this is a specific humidity anomaly field. You can see moistening in the upper levels and drying at low levels associated with the mesoscale saturated downdraft. And the next. This lower plot shows the relative humidity anomalies showing, actually, this is the total anomaly field, a total relative humidity field. And you can see very moist conditions in the upper troposphere near the stratosphere associated with the leading anvil, as well as moist conditions connected with the stratiform region. Next. Okay, now continue with the composite. If you click on the next, the upper panel here shows the vertical motion field. And in the stratiform region, there's upward motion aloft and downward motion below. Next. This is the apparent heat source field. You can see strong heating in the stratiform region, and then there's less heating at low levels. In fact, even cooling in the stratiform areas in some locations. But there's a strong vertical gradient in the heating near the melting level, which is indicated by that dashed line. This strong vertical gradient in the heating is due to the cooling from melting that exists. And that strong vertical gradient in heating rate is important in creating potential vorticity, as we'll see in a moment here. The lower panel is the next is the apparent moisture sink, which shows large values in the stratiform region. Next. So we've taken, out of those 12, we looked at the 7 northerly track squall lines, of those that track just south of the African easterly jet, which resides around 15 north. So on the cyclonic shear side of that jet, we've taken 7 northerly track squall, the strongest, and put them together in this composite. So if you go to next, these are total fields now. You can see there's divergence aloft in the stratiform region, and then there's convergence near the melting level. Next. The absolute vorticity field, there's an anticyclone aloft and cyclonic absolute vorticity near the melting level. And next, this is the PV, this is a total PV field. You can see between 400 and 500 hectopascals ahead of the convective line, there's high PV, and this is associated with that tongue of PV that extends southward from the Sahara region. But you can see it gets amplified and deepened following the squall line passage. So there's something going on with this squall line that amplifies the potential vorticity field in the mid-troposphere. Next. This is another figure that shows the composite structure for the 7 northerly tract cases. But in this case, we show the anomaly fields. Next. There's a vorticity maximum anomaly near the level of the African easterly jet, around 700 millibars. And this is on the cyclonic side of the African easterly jet. So basically, as the squall line moves by, there's a circulation that comes in that sort of intensifies, amplifies the vorticity several, say 6 to 12 hours after squall line passage. Next. This is a lapse rate anomaly. Basically, the high values here mean increased stability. So where there's melting, there's an enhanced layer of stability in this region. Next. And this is a PV anomaly map. There's an upper level, or at least around 400 to 500 HPA. There's a positive PV anomaly, and this is connected with the heating over the Sahara. Next. And a little bit lower, residing near the melting level, which is indicated by the dashed line, that's 0 degrees C, there's a PV maximum that shows up there connected with the melting. So we have sort of 2 sources of PV coming into the picture here. Next. So we put together in a summary here a sequence of slides going from 24 hours on the top to 24 hours before to 24 hours after squall line passage at Niami. So on the left side there's PV anomaly field is shown in color at 700 HPA, as well as the circulation anomalies. And the sounding arrays are shown with the star indicating Niami. And in the green segment is the schematic squall that's approaching the region. It's not always that structure, but it's shown for reference. And next. You can see there as squall line moves past the MIT radar site, there's a circulation center to its south, and that's at around 700 level. And it moves off toward the west following that squall system. Next. This second row of panels is the flow at 600 HPA. The melting level is at around near this level. It's actually 575 HPA. So this is near the melting level. And you can see this, the structure with PV is different this time. As you go after the squall line passage, the Niami site, you can see a wake of high PV, and that's connected with the melting in the stratiform region that covers a huge extensive area. Next. I've repeated the panels at 600 on the left in this slide, just what we saw before, showing this large wake of PV behind the line. And on the right is the same panels, but at 500 HPA. And if you hit the next, you can see here, there's PV anomaly that extrudes down from the north into the region, and eventually at 24 hours, enters into the region just behind the squall line. So here we have two features, different source, two PV sources. One is associated with melting, and another appears to be anticyclonic Rossby wave breaking. Although we need to look into this in more detail, go by looking at analyses farther to the north, that comes into the region and amplifies the PV behind this squall system. Next. So to summarize here, we have a composite that shows that if we look at the composite PV structure, we see an enhanced PV behind these squall systems. And by the way, two of these squalls became tropical cyclones, Debbie and Ernesto. And it's the merger of the PV anomalies from two sources, one associated with the melting that extends this PV anomaly a little bit lower down, and the other from the Saharan heat low, basically area that has the PV increase higher at a higher level. So you get an expansion and strengthening of the PV anomaly, which could potentially then provide for more potent seedling disturbances for Atlantic tropical cyclone genesis. Perhaps a mechanism seen in the northern part of the world because of the unique situation over West Africa. So the last slide is this one here. Next. We've looked at convection connected with African easterly waves, and it typically takes the form of squall lines with leading convective lines and trailing stratiform precipitation. The radar and sounding data from the AMA are used to investigate the characteristics, and the composite of AMA squall system reveals a prominent mid-tropospheric positive PV anomaly in the trailing stratiform precipitation region, which has two sources, a squall line dynamical microphysical processes, namely melting, and secondly, deep atmospheric boundary layer of the Sahara layer, which gets pulled into the squall system from the north. The merging of these two anomalies can yield potent incipient disturbances for TC genesis over the Eastern Atlantic. Thank you.
Thank you very much, Dr. Richard, Dr. Johnson, for that very insightful account of the way West African monsoon is manifest. I think this is very detailed, and in fact, I'm amazed that the AMAP data is still feeding so many studies in helping us understand the West African monsoons. This is great. We actually ran out of time, but at the same time, I think we can take one quick question if anyone has from the people who have joined the WebEx session. Madhu, you can unmute yourself and ask your question.
Yeah, good morning, sir. Very good presentation, sir. I would like to ask that this mid-level potential vorticity plays an important role where it's connected to the mid-level moistening through potential vorticity, because of the vorticity causes the merging of many clouds. I just want your view on that, sir. Thank you.
I'm not sure I fully understood a question about the what role does moisture play? I couldn't quite follow the full question.
The potential vorticity in the mid-levels connected to the moistening of the mid-levels or the African, like 700 to 600 hectopascal. The moistening of that thing is a preconditioning for the convection invigoration there.
I must apologize. I still couldn't quite get the question, but let me answer a point on a different thing. Perhaps it is of interest to the Indian monsoon. These monsoon depressions, I think, have a lot of stratiform precipitation, and this similar process may play a role in helping to spin up these circulations.
Yeah, maybe Madhu, you can probably put your question in the chat box and then get the answer during the course of this session. So now we will move on. Thank you again, Dr. Johnson, for that excellent presentation on the West African monsoon. Now we move on to the next presentation by Dr. Mrityunjay Mohapatra, who is the Director General of Meteorology, India Meteorological Department, and also the permanent representative of India with WMO. In fact, he will be getting into another important aspect, that is impact-based forecasting. Dr. Mohapatra is very well known for his contributions to cyclone forecasting. In fact, he is popularly known as the Cyclone Man of India. So he actually will be talking about the monsoon forecasting on short to medium range scales and how impact-based forecasting is happening, and what is the current progress and what are the plans. Dr. Mohapatra, the floor is yours.
Thank you, Dr. Kumar and distinguished panelists. Once again, I convey my greetings to all the distinguished delegates and participants for this international workshop on monsoon and for this special session on regional monsoon. So I'll be talking about the short to medium range impact-based forecast of monsoon in India, the progress and plans. My slide is moving, Rupa sir.
Yes, sir. Yes, sir.
Yeah.
Fine. So of course, know that southeastern monsoon is a predominant weather system affecting all socio-economic activity in the region. And the southeast monsoon starts in the month of May and continues till the middle of October. During this period, as the monsoon intensifies gradually and moves towards the north, we encounter a number of severe weather events. To top all the severe weather events, we experience the heavy rainfall leading to thunderstorms, floods, and landslides in different parts of the country and this region. We also experience the thunderstorms associated with weather like lightning, gusts, squall, and dust storms. And there are many low pressure systems developing during monsoon season that includes low depressions and cyclones. During onset phase of monsoon, we also experience the heat wave conditions, and sometimes during the break monsoon conditions, also there are heat wave conditions. The heat wave conditions aggravate during monsoon, especially over northern parts of the country, when you have the monsoon because of the combined impact of temperature and relative humidity. As you can find out from this graphics, that the southeast monsoon for the country contributes about 70 to 90%, on the average it's 74% of rainfall during this June to September, if you consider. Then if you consider the interinal variability of monsoon, you will find that though there is an assured rainfall of about 88 centimeter over the country as a whole, it has a variation of 10% for the country as a whole, but spatially there is a large variation from west to east and from north to south. The monsoon is orographically dominant and hence leading to many severe weather events in the orographically dominant regions like the Himalayan region and the Western Ghats and Eastern Ghats. So if you just look at over the years, the monitoring and forecasting in the short to medium range, you will find that there has been a significant improvement with respect to all these severe weather events which are occurring in monsoon season. Especially if you talk of the cyclones, yes, there has been almost zero error in many extremely severe cyclone storms passing over the area in the recent years. As a result, it has led to the minimization of loss of lives and properties. You can find out an example here, the super cyclone Amphan, which crossed during the onset phase of monsoon in 2020 May. You will find that it was well predicted, not only with respect to genesis, but track, intensity, and associated severe weather. There has been about 40% improvement in accuracy of various types of severe weather events, including monsoonal heavy rainfall, the cyclones, the heat waves, and the thunderstorms in the recent 5 years compared to previous 5 years. You can also find out monsoonal heavy rainfall. We stand at now about 75% accuracy in 24 hours ahead, and 60% accuracy 5 days ahead in predicting the occurrence of heavy rainfall. Similarly, thunderstorms we look at, we can predict the thunderstorms about 85% POD 1 day in ahead, and also 3 hours ahead in the non-casting scale. So when we have got such a good forecast accuracy, but still what we find that the loss of property continues. So now the question is, why the good forecast result in poor response? An accurate and timely weather warning does not guarantee always the safety of lives. I'll show some examples. It is mainly because the weather models and other hazard models are not coupled every time. And there is lack of scientific and technical capacity to translate the hazard information into the impacts. There is inadequate communication channels which can fail during the event to reach out to the last mile. And there is lack of appreciation and utilization of available vulnerable informations like maps, geophysical, geospatial, with higher resolutions. And also, many countries and many times with the specific severe weather, we may not have the effective decision support system. So that's why if you just find out the impact of, for example, the cyclones losses in different countries in the Southeast Asian region, you'll find that there's a huge loss in terms of the absolute value, also capital and other social losses. So if I take an example of the severe weather events, this is the cyclone Titli, which crossed northern parts of Andhra Pradesh during the withdrawal phase of monsoon in the month of October with the monsoonal gyre. And we could provide a very good forecast about the track, intensity, landfall, but still 77 people died in Odisha because of the landslides. So landslide, there was no prediction mechanism, and hence the impact in terms of the severe weather of landslides would not be provided to the people, and hence people got trapped in the landslides. Similarly, if you just consider another example, in 2013, the Kedarnath floods in Uttarakhand of India, there also you will find that though there was forecast, but the impact forecast was not there. Hence, people could not understand and could not take action to minimize the losses, and more than 4,000 people died in one event. Now, if you just considering all these things, so what we want actually, we want a paradigm shift from a simple forecasting to the impact-based forecasting. So from information-based forecast to the impact-based information and risk-based warning. So for this purpose, we not only need observations, forecast, and warning, but also we need observations, forecast, expected impacts, and risk-based warning. So to carry out this, so what the issues, if you look at the issues, firstly, there is a challenge. Then because you are shifting from simple forecasting to the impact-based forecasting, then it comes the methodology. The methodology differs from country to country and over the period of time also. Then you need some kind of solution towards the decisions, and you have to practice whatever you introduce operationally. So objective is that the weather forecast is being converted to impact forecast, which will help in hasty decision to a well-prepared decision by the disaster managers. While doing so, we have to go for an integrated data system, data utilization instead of the isolated data. Then we have to go for an interactive mechanism instead of only broadcasting the information to the disaster managers, the general public. And above all, we should keep user-first design concept. So far, many national meteorological and hydrological agencies, they feel the priority in formulating their weather forecast without taking into consideration the user's mindset, user's design, except the user's expectations. So the impact forecast starts with user's first design concept. So therefore, we will be converting the weather information into the response mechanism through weather translation and impact estimation. So therefore, as a weather forecaster, we might be feeling that we have a lot of information which will be useful to the user, but user feels they have got a lot of information which is not linked to the weather at present. So therefore, these two wedges of green and orange, they have to merge with each other so that they can work together, becoming a rectangle. So what we need therefore actually a collaboration mechanism among the weather forecasters and the risk managers to have a realistic risk-based warning. So in this background, India Meteorology Department has taken up the steps for implementation of the impact-based forecast. during monsoon season especially, and also for other seasons. So what we do in this, actually we try to understand the warning needs for early actions through various meetings with the National Disaster Management Authority, State Disaster Management Authority. Then there we go for partnership and collaboration with many agencies within the country and outside. At the same time, we go for hazard forecasting. We try to prepare various types of severe weather indices and hazard modeling. It goes towards the risk assessment. Then we assess the likelihood impact with the probability forecast and many other. And by that, we come for the level of impact. So considering all these, left-hand side, right-hand side, as it is shown here, we go for the impact forecast, then we go for dissemination, then prepare for the early action. Then, of course, we have to go for verification, review, and improvement of the system. So when you consider all these things, we are following the 4 standard methods. The first method we adopted is the threshold method, that is define a forecast threshold at which people or infrastructure in a specific location are expected to be negatively impacted. Then you go for the second method, that is qualitative combination method, where we create a composite index that combines relative vulnerability with forecasted hazard magnitude and create a relative priority. Then third method, we go for the impact modeling methods. There, what we do actually, we combine the hazard magnitude with the vulnerability and exposure to predict the level of impact. And finally, we go for the climate sensitive method using a combination of the socioeconomic baseline data and climate data, and identify the areas where vulnerability is most closely correlated with the forecasted climate risks. So if I look at all these things where we stand now, for stage 1 forecast, that is stage 1 impact-based forecast, we started very early. For example, in 2013, we started this color-coded warning for the heavy rainfall during monsoon season after the Kedarnath episode. Every disaster gives a lesson. After that, we started this one, and this was just based on the simple mechanism of giving heavy rainfall, very heavy rainfall, and extremely heavy rainfall, and giving a color code just based on the own experience of the forecasters. So by that way, we just made a beginning about the heavy rainfall impact-based forecast. But in the stage 2, we came up with some kind of qualitative combination with the different types of thresholds. So we defined whether it will be 1-day rainfall, whether it will be the composite of 2 days rainfall, and by that way, we could find out the hazard modeling and hence the expected impacts. In the stage 3, if we just look at, we went for implementing the impact-based forecast for heavy rainfall during monsoon season in 4 stages. We issued 48 hours in advance or 3 to 4 days in advance a heavy rainfall watch at the district level. So all the districts in the state were given the warning about the impact expected due to the heavy rainfall. Then it was followed by the stage 2, that is heavy rainfall alert 48 hours in advance, then heavy rainfall warning 24 hours in advance. In stage 4, 12 hours prior to occurrence, we started giving every 3-hour informations. So while doing all this in the stage 3, what we do, right, we collected the climatological data of the past impact based on different thresholds. The climatological impact expected we consider based on disaster weather events published by India Meteorology Department since 1980s. So all these helped to have some kind of impact matrix at the district level and at the city level. And accordingly, impact was provided. So therefore, by 2020, we could come up, in spite of the COVID scenario, some kind of standardized standard operating procedure for 4-stage impact-based forecast at capital cities and all the districts. Then we went for stage 4 in 2021, partially dynamic impact-based forecast. Here, all districts throughout the country were provided based on certain dynamical information generated. I'll show you certain examples. We considered climatology, considered geophysical information, exposure, vulnerability maps, etc. And hence, we have now a GIS-based platform with all this data, and where we can merge the information and take a decision. So this is just an example what we do with respect to monitoring the heavy rainfall, so that We can provide realistic information every 3 hours to the general public and disaster managers. Then we went for predicting the rainfall. A lot of information has been developed recently by the dynamical statistical modeling, ensemble modeling, and also the multimodal ensemble scheme of Ministry of Power Sciences involving IMD, IITM, and National Center for Media Management Weather Forecasting. All these are being utilized to have a realistic forecast and hence the guidance for the impact. So if you just look at the module what we have developed for impact-based forecast of heavy rainfall during monsoon season, here we'll see that we have considered the not only the immediate rainfall, but also the past few days rainfall is accumulative, assess the soil moisture, and assess the standing water, and hence the impact of the forecast rainfall. So we consider the climate extremes also, we consider forecast up to 5 days rainfall, and then we go for sector-specific products in the production module and standardized SOP and customized bulletins. In the meantime, also we went for capacity building by conducting the training for the forecasters and the stakeholders. So if you just look at the same thing, it is represented here. So what we do actually, we consider the administrative layers like state, district, city, ward boundary, then digital elevation models, land use, land cover data, rainfall data, infrastructure layers, demographic data, then major point of interest data like school, college, hospitals, airport, bus stand, communications, etc. So these are all under development, but to a large extent we have developed the framework as it is on here. Now, if you just look at some of the data what we've collected, it is very difficult to collect data for impact-based forecast. So what we have done actually, we have gone for 2 sources. One is the open source data set, pan-India, it's shown in the left-hand side figure. Another one is the government sources as data collected from state governments and other agencies. You can find out that data collection is picking up, the entire country is still not having all the data. We consider all types of exposure conditions as mentioned here, up to the power sectors, communication sector, tourist spots, water bodies, transport sectors, and many more. So if you just look at an example of the impact of heavy rainfall, the hazard modeling, or impact modeling, what we have done actually, apart from all these heavy rainfall forecasts, we've gone for urban flood modeling. So starting with 2 cities, we have taken up Mumbai and Chennai, where urban flood modeling has been demonstrated with all the socioeconomic data and being provided in case of anticipated heavy rainfall. To take care of the flash flood which occurs during the monsoon season, especially over the hilly areas, we have a South Asia flash flood guidance system where we provide the guidance for next 48 hours, 24 hours, 12 hours, and 6 hours in terms of flood depth, flood threat, and the flood risk. For riverine flooding, Central Water Commission and India Meteorological Department work together, and with the prediction of heavy rainfall and quantitative precipitation forecast, the color-coded impact-based forecast is being provided by the Central Water Commission of Ministry of Water Resources, Government of India. There I just want to mention there is involvement of the stakeholders in the form that National Disaster Management Authority, India Meteorological Department, and Central Water Commission meet together every day through video conferencing and formulate the impact expected due to the flood over a river catchment. Now coming to the cyclone which occurs during monsoon season, especially during onset phase and withdrawal phase, so we have a very systematic approach over the period it has developed. We have a genesis forecast 15 days ahead, then 5 to 7 days ahead, we have the medium range forecast, then it follows with the track forecast, intensity forecast, structure forecast, landfall point and time forecast, adverse weather warning, and damage expected and action suggested. And the forecasts are very user specific and sector specific. It goes to all disaster managers, the coastal shipping, port warning, fisherman warning, aviations, public, media, etc. in different stages like pre-cyclone watch, cyclone alert, cyclone warning, post-landfall outlook, and of course the de-warning. While picking the impact-based forecast in 90s, we went for the historical damages with different stages. Just based on the different stages of the intensity of the cyclone, we could find out what is the damage expected and action suggested. Initially, it was adopted in 1990s, but over the period, it has been formulated and reviewed as per the expectation in consultation with the disaster managers. But finally, in the recent years, we have got a dynamic impact-based forecast system. And just give an example of the cyclone Amphan, which was a super cyclone and crossed West Bengal and adjoining Bangladesh coast on 20th May during the onset phase of monsoon. You can find out that the first and foremost requirement for impact forecast is the realistic, reasonably correct track and intensity forecast. As you can find out, red one is the forecast track, black one is the actual track. They were almost coinciding with each other 5 days ahead, and that gave a enabler, that become an enabler to take the impact forecast seriously by the disaster managers and to take actions. So if you just find out the severe weather and the impact expected with the cyclones, these are mainly the heavy rainfall leading to floods, and you have got the winds leading to damages, the structure, and the storm surge leading to coastal inundation. This is just an example. You can find out that we have done, first we have done for climatological hazard analysis. We have identified the various districts which are prone to the storm surge hazards or wind hazards or the maximum precipitation hazards. On the left-hand side, you can find the maximum probable precipitation which is expected with a cyclone. On the right-hand side, you can see the flood zones in Amphan and the affected population in Amphan because of the floods. And on the bottom, you can find out what are the various types of socioeconomic attributes which are expected to be damaged by the cyclones. All these attributes are being prepared on real time and being provided to the district collectors and the state authorities and national authorities to take preparatory actions. And you'll be happy to know that based on these, nowadays, Government of India has introduced the response mechanism in which the financial forecast is being provided based on this, and government sends money to the states prior to landfall of the cyclones. Now, if you just look at the wind, you can find out that India Meteorology Department is a very good mechanism for monitoring the wind and its impact. All types of platform, including satellite, radar, coastal observations, climatology, are in hand, and we provide the forecast for 28 knots, 34 knots, 50 knots, 64 knots. I want to say that unlike other ocean basins, here we provide the wind speed forecast more than 28 knots. It's mainly because that our ocean basin is strong, small, and also the fishermen here are poor comparatively, and therefore boats cannot sustain even the wind more than 28 knots. So therefore, this type of wind impact forecast helps the fishermen to save their property and also to save their lives. Now, if you just look at the wind hazard analysis, for example, Amphan, this left-hand side diagram is the probable maximum wind as per our analysis for different districts along the coast. And here is an example of the wind speed forecast and impact over the West Bengal due to the cyclone Amphan. You can find out how clearly this GIS-based dynamic risk assessment atlas is bringing out the expected impacts. Now, this is an example of the storm surge modeling, impact modeling, and hazard analysis. On right-hand side, you can find the probable maximum storm surge analysis based on the long-term data. And here we have got three models. One is the nomogram, other one is the storm surge model developed by IIT Delhi. Then we have got INCOES advanced circulation model to provide the coastal inundations. All these three are being utilized to provide inundation. And this is an example of inundation provided during the cyclone Amphan for the coastal districts of West Bengal. And accordingly, the different structures and different facilities and utilities which are exposed to these storm surge that were predicted, and information are available to the government and other agencies to take the actions. Now, coming to the another important hazard which occurs in monsoon, that is the thunderstorm. You know that in the thunderstorm we have the lightning, we have got the squalls and gustiness, we have got the hailstorms, and also we have got the floods sometimes because of the heavy rain, especially in northeast India. So therefore, the vulnerability are quite high due to the lightning and other hazards in a thunderstorm. You can find out, I have just noted down here the various types of impacts of the thunderstorm associated weather which made people vulnerable. So what we did actually, we started initially with a threshold mechanism, giving the different colors like green, yellow, orange, red, depending upon the winds associated, depending upon the expected gust and squalls, and depending upon the hailstorms and etc. We also consider what is supposed the climatology of various parameters like hailstorm, duststorms, tornado, strong winds, etc. By that way, we could find out some kind of vulnerability mapping by considering those winds which has led to the damage to the structures and loss of lives. That is also mapped. And this is just an example how the hazard modeling has been done for thunderstorms with respect to dynamical models and also with respect to observational data sets from satellites and radars. So what we do now, actually, all these informations are being integrated with the socioeconomic attributes as it is shown for the monsoonal heavy rainfall and the cyclones. So this is just an example how the dust storms can also have the impact along with the hailstorms and floods. So this is another example of what we are doing actually. We have developed some kind of vulnerability atlas of India at the district level and also the city specific level. We have developed the climate hazard vulnerability atlas of India by IMD, as you can be seen in this diagram here. it provides the vulnerability due to various types of thunderstorms, lightning, dust storms, and hailstorms. Now, last but not the least, that is the heat wave conditions. As you will all know that India is very prone to high temperatures, especially in the month of June, July. And for that purpose, we continuously monitor and provide some kind of heat wave warning. And at present, we have a heat action plan across the country and for all the capital cities, where we provide the information about the heat wave and expected impact in collaboration with various health agencies, state government agencies, central government agencies, and municipal corporations. This is just an example of the heat wave warning in a multi-hazard map. To further aid the vulnerability assessment and hence the risk, what we have gone for, that we have prepared the wind impact and relative humidity impact. We have calculated normalized vulnerability index of the heat wave and also the climatology of heat wave based on long period data. As you can see, this is the month of June. All these informations are for the month of June, for example. You can find out the central part of the country, how vulnerable it is towards the heat wave conditions, even there is monsoon. We also try to develop some kind of heat hazard analysis for the month of June, as it is shown here, considering various parameters. So, for example, consider only maximum temperature or minimum temperature, duration of heat wave, relative humidity, and wind speed above normal temperature days, and sum of all the weights we consider, and to find out, to try to zonation, to do a zonation of various types of districts in the country, depending upon all these parameters. So finally, we have come up with GIS-based heat wave informations, where we have the socioeconomic attributes. For example, it is shown here, Indian railways and national highways. There is transport sector which is affected by the heat waves. If there is a train passing from Delhi to Kolkata, and there is heat wave conditions across the road, then the authority has to make arrangement for AC conditions, the water conditions, drinking water especially, and other arrangements. Individuals also make arrangement for that purpose. Therefore, the socioeconomic attributes leading to this impact-based forecast of heat wave, especially the monsoon season, is certainly helping the people to minimize the loss of lives. As all of us know, the number of loss of lives is reduced significantly due to the heat wave also. There was only 4 deaths last year compared to 2,000 deaths in 2015. Now, while summarizing, I'll say that IBF in India Meteorology Department has come up a long way with respect to methodology. We have come up with the objective methodology and objective hazard modeling, impact modeling, and we are in the process to add the socioeconomic attributes. So there has been some color coding to begin with. Then we have gone for introducing the temporal range up to 5 days. Then spatial range have gone up to location, city, districts, and region level. Forecast have gone up to probabilistic forecast modeling system. Then hazard type, we have considered all types of hazards as mentioned here. And language, we have come up with initially English, but now we have got tri-language, that is English, Hindi, and the local language. All the sector-specific informations are being provided almost in a semi-automatic method, utilizing all types of dissemination in local language that is helping the local media and the people. So if we just look at the future plan, this stage 4 of the impact and risk modeling, which is going on now, it will improve further. And by 2025, we should have a reasonably accurate impact-based forecast and risk-based warning system in the country for all types of severe weather up to 5 days at station level and at the district level. Now, if I just look at another challenging for this purpose is the decision support system, which is underway to develop for each and every individual severe weather. And then, of course, we'll go for a multi-hazard warning system. So if I just look at, while introducing all this thing, verification is very important. And at present, we do not have a quantitative verification of the impact-based forecast that we introduced from next year. So thank you very much for giving this opportunity to speak on this evolving impact-based forecast risk-based warning system in India. Thank you.
Thank you very much, Dr. Mohapatra, for that very comprehensive and really interesting presentation. In fact, this actually is very encouraging that we are now finally able to achieve the full value chain benefits of weather and climate services. But of course, the real challenge is actually to get a handle on vulnerability and exposure, as you have rightly highlighted, which actually is based on human systems, and it may be quite a big challenge for us, for meteorologists, to actually get into. So we definitely need partnerships with the concerned stakeholders. Unfortunately, we ran out of time completely. In fact, we are now behind, but at least if anyone has a burning question, probably one question we can have before we break. I see no hands. So thank you very much, Dr. Mohapatra. And we thank you for this very informative talk. So now we will have a break for about, since we are behind the time, we'll break for about 10 minutes.
Yes, sir. Yes, sir.
Yeah.
10 minutes.
Yeah, we'll reconvene at
10:15 local.
yeah, 10:15 local. That will be 4:45 UTC.
Okay. Hi. Good morning, good evening, good afternoon.
Good morning.
Okay, good morning.
Here it's almost 2 a.m.
Oh, okay.
It's not a very easy time to give
Start.
a talk.
We start?
Yeah, I
Nice.
can.
Well, could you just remind me how to share? So I have to share my
Full
screen.
screen. Yeah, full screen you share.
So here. And now what do I do?
Then you go to your PowerPoint and
No. First you share the screen, madam.
Pardon?
yeah.
At the bottom
Share
of
the
the screen,
screen.
you can see three options: mute, start video, and share. So click on the share.
I'm trying here,
But since the presentation is already,
Or shall we
the
load the
organizers,
presentation
they
for
can
you?
share it if you like.
it says I tried last week and it worked. No, I don't.
Alice, no?
Hmm.
Maybe the organizers can share, Alice.
Yeah, we can share from our end.
You can join
I would rather
Yeah.
control the presentation.
Yeah, that is true.
Uh,
This is who has shared? You have shared, our organizer has shared this one. Somebody.
So, madam, at the bottom of this app, you can see
let's
three
see.
options: mute, start video, and share.
Start. Now the video is already on.
Share.
And one more option, share.
Do you see a button called share with an arrow, upward arrow? It's in the bottom.
Yeah, I have already
You click on the share button.
chosen, yes, click it on this option. But I don't know why.
Are you getting any permission issues?
So I should choose full screen or just a window?
The leftmost panel, you can see screen 1.
Or full screen, that is better.
Yeah, I am clicking on the full screen, but nothing happens.
By clicking leftmost panel, then there is one more click you need to do, share.
Oh, it
Or
doesn't.
Can you
Yeah.
share from our end?
I see and I click on the options, but nothing happens. So perhaps we then get the presentation from your side then.
Okay. Busher, can you share? Yeah.
I think that is better. Okay, welcome back everyone. For the next presentation, we go to the another aspect of regional monsoons in terms of the American monsoon. So we now have Professor Alice Grimm, who is a full professor in the Department of Physics in the Federal University of Paraná in Brazil. So she will be speaking about interannual.
Now, okay.
So she will be speaking about interannual and intra-seasonal variability of the South American monsoon. Professor Grimm has a long experience in working on the American monsoons, and she is well known. She's also served as a member of the WCRP Clive Chuvek's Monsoons panel. We look forward to her presentation on the South American monsoon. Professor Grimm, the floor is yours.
Thank you. Good morning to everybody. I will talk about the combination of interannual and intra-seasonal variability of the South American monsoon, focusing on the MGO modulation by ENSO. Next, please. Here you can have an idea of the intensity and of the extension of the South American monsoon. From the annual cycles of precipitation, you can see that most of South America is dominated by a monsoon regime with much rainfall during summer and almost no rainfall at all in winter. And in the figure on the right, you can see the monthly average of precipitation in several monsoon core regions around the world. So you can have an idea of the intensity of the South American monsoon. Next. Well, let's first give you an idea about interannual variability in South America and of an idea of the importance of ENSO for this interannual variability. So here you have the continental modes of interannual variability for total annual rainfall and seasonal rainfall. Only the first modes, just for summer, we are showing the two first modes because summer is our focus in this presentation. In all these first modes for annual total, winter, spring, autumn, you can see a very strong influence of ENSO on these first modes of variability. Here in the summer, when I talk about summer, I am referring to austral summer. It is the second mode which is related to ENSO, and it doesn't impact very much on the core monsoon region actually. But the first mode has a very high factor loading on this core monsoon region, although it is not strongly connected to a well-known SST pattern. Next. The mechanisms for ENSO impact on South America are local forcing, as in Western tropical South America, and atmospheric teleconnections, which actually are the main mechanism of the influence of ENSO on South America. These teleconnections can follow a tropical pathway through equatorial, Kelvin and Rossby waves, which change the Walker circulation as in eastern equatorial South America, and an extratropical pathway through Rossby wave trains, which produce which are produced by Pacific tropical convection, and this extratropical teleconnection change circulation and precipitation here in subtropical South America. Next. Next, please. Besides teleconnections, another mechanism of variability of rainfall in South America is surface-atmosphere interaction. There is a relationship between precipitation in spring and summer in such a way that there is a tendency to reversal of anomalies here in this region, in this core monsoon region, from spring to summer. There are significant correlations between these modes in spring and summer, and a mechanism, an explanation for this tendency to reversal was tested with regional model. Next, please. Well, and this can also be seen here in the evolution of precipitation in central East Brazil compared with climatological precipitation evolution. Next. Here we have then for December, January, and February, the anomalies, the precipitation anomalies during El Nino. We have below normal precipitation in the Northeast, South America, and above normal here in Central East and Southeast South America. In the opposite, more or less, during La Nina. Next, please. Next. So let's introduce the intra-seasonal variability in South America. Here we have the contribution of synoptic and intra-seasonal timescales to total variance of summer rainfall in South America. You can see that intra-seasonal variability has a great contribution here in Central East South America. It's a very significant contribution, while synoptic variability has a much stronger contribution here in the western part. Looking at the intra-seasonal variability here in this region, it's possible to see that this variability has components in three main variability bands, from 10 to 20, 20 to 30, and 30 to 70 days. And the spectra of this intra-seasonal variability in this region shows that compared with the reference red noise, the Madden-Julian oscillation, which is here in this band, has a very significant contribution. Next, please. The first three rotated modes in the intra-seasonal time scales are these ones. So we have the three modes are actually among the five first modes of all these in these three bands, time frequency bands. So these two first modes are dipole-like modes. One with highest factor loadings here over the South Atlantic convergence zone. Next, please. And here in this 30 to 70 day band, it's possible to see it's the first mode, and this is the second mode. And this mode here, this second mode is connected with equatorial circulation, either a westerly or easterly regime for wet and dry phases, whereas this mode here is connected with extratropical perturbation. Next, please. Next. So let's first take a look at the Madden-Julian oscillation impacts in average over all three possible ENSO states: neutral state, El Niño, and La Niña. So without discriminating by ENSO state. So we can see that the the strongest convection, it propagates from the Indian Ocean till Central Pacific, where it extends southeastward here in the South Pacific, in the subtropics of the Central East South Pacific. And when this happens, starts enhanced convection over the Central East South America, which reaches its maximum in phase 1 of MGO. Next, please. When we have this enhanced connection here or suppressed convection in phase 4, there is also in the subtropics, in South Pacific here, strong low-level convergence here and low-level divergence here. In these regions, in the subtropics of the Central East South Pacific, are, according to analysis of influence functions, very efficient regions in which anomalous upper level divergence or convergence are very efficient in producing extratropical teleconnections towards South America to produce circulation anomalies and precipitation anomalies. Next, please. Next. Well, here we can see that, oops. Let's look just at, well, here we can see then this in phases 3 and 4, low-level convergence here, and in phases 7 and 8, low-level, high-level, this is high-level divergence, and here high-level convergence, associated with suppressed, here in this case, with suppressed convection, and here enhanced convection. Next, please. Well, here it's possible to see that while you have this anomalous convection, upper level divergence in the equatorial belt, and not much anomalous convection in the subtropics, there is no pattern of extratropical teleconnection here over the Pacific. But when this upper level anomalous divergence extends into this influence region here in the subtropics, extratropical teleconnection starts forming here. And it's delineated in phase 8, start forming in phase 7, delineated in phase 8, and fully established in phase 1, when the anomalous convection over South America is at its maximum. Next, please. And then in phase 1, we have the highest precipitation here, which can reach more than 4 millimeters per day, the anomalies filtered in intra-seasonal band, so anomalies from other sources are not included, and this represents around 35% of climatology. So it's a pretty strong impact. And in these other phases, we have suppressed convection. Next, please. Well, these, which of these anomalies, convection anomalies here in the Pacific, are responsible for forming this wave train here, responsible for these anomalies over South America. We used this upper level divergence as forcing in a simple model, and we are able to reproduce this wave train with anticyclonic and cyclonic circulation here. But what exactly, which of these anomalies is responsible actually by these circulation anomalies over South America? So looking at influence function, for these two action centers here of this anticyclonic and cyclonic circulation here, we see that in this region here, where there are the strongest convection anomalies, this region here in the subtropics of Central East South Pacific, this region here is the most efficient region to produce these two circulation anomalies. Next, please. And this is confirmed with simulations using as forcing only parts of these convection anomalies. So using this one, we don't get the right anomalies over South America, neither from this or the combination of the two. But when we use this here in the subtropics of the Central East South Pacific, we get exactly this wave train connecting to South America. So the most important convection anomaly is not the strongest one, is that one which is situated in a region of the highest influence. Next, please. So now let's see what ENSO changes in MGO. So first, let's see, just a moment. Let's start with the ENSO influence on the frequency of MGO phases. So here we have the relative frequency of MGO phases during El Niño, La Niña, and neutral years. It seems that the background ENSO-related anomalies influence the relative occurrence of MGO phases with similar patterns of circulation or convection anomalies. For instance, MGO phase 1, here on the left, it's relatively more frequent during El Niño and shares some common features with El Niño. For instance, suppressed convection over the equatorial Eastern Indian Ocean and Western Pacific and maritime continent here, while enhanced convection predominates over the equatorial Central Pacific, which is something that is observed here during El Niño. On the other hand, the phase 5, which is relatively more frequent in La Nina, displays opposite common features with La Nina. Next, please. Well, in ENSO states, how ENSO states affect the MGO propagation. Here we can see that quicker, well, we know from previous work that quicker or slower propagation is expected for weaker or stronger convection. During La Nina, the stronger convection here over the maritime continent, here the Eastern Pacific and the Western, the Eastern Indian Ocean and Western Pacific, this stronger convection is consistent with slower eastward propagation, as can be seen here, comparing with El Nino. During El Nino, the anomalous convection over the maritime continent is weaker and does not reduce much as it moves over the maritime continent to the Western Pacific. And it extends further during El Nino into the Central Pacific. Yet during La Nina, the zonal wind anomalies, they propagate quicker over the colder East Pacific, and anomalous convection is earlier established here over South America than during El Nino. During El Nino, the highest convection anomalies happen in phase 1, and during La Nina in phase 8. Next, please. Well, here we can see some features comparing of OLR anomalies, comparing for El Nino and La Nina, these OLR anomalies. So we can see that during phases 8 here, phase 8 and 1, when MGO displays enhanced convection here in Central Pacific, which is something in common with El Nino, and these anomalies are enhanced here. While during La Nina, they are really not enhanced. They are weaker. For instance, let me show just one more example here. Here in phase 5, 6, during El Nino, we have a propagation of this enhanced convection across the dateline, whereas in La Nina, it doesn't happen. The convection propagates only in the subtropics, but during El Nino, it propagates across the dateline and is very enhanced here in phases 8 and 1. As a consequence, this anomalous subsidence over Northeast South America, which happens in phases 4, 5, and 6 of the MGO. This is enhanced because of this enhancement of this convection in Central Pacific. So subsidence here is strengthened. And during La Nina, this subsidence here disappears. So we have even enhanced convection here. So this influence of the background state of ENSO can, and there are many other examples, can change this anomalies associated with different phases of MGO. Now, let me emphasize that during phases 7 and 8, and here, and also here, there is an enhancement
Please,
of this
excuse me, Alice.
anomalous convection. Pardon?
Excuse me, I think we have to wind up because I think we are running out of time. Thank you.
Well, next, please. I just wanted to emphasize here that is subtropical convection, which is important to establish this teleconnection towards South America. It is enhanced not only during El Nino, but during La Nina. It's a non-linear effect. This here is the difference between the anomalies in El Nino and neutral years. And you can see that in both cases, this subtropical convection is enhanced. And the wave train is well defined during El Nino and La Nina, while in neutral years, it's very weak. Next, just to show the effect here on precipitation. These here are anomalies of precipitation, of observed precipitation. It's not OLR, where we can see the effect of enhanced subsidence here over during El Nino, here over Northeast South America, whereas during La Nina, you can see that the subsidence is weaker, and we have even enhanced precipitation here. And due to this enhancement of the teleconnections towards South America, we have much stronger precipitation anomalies here in Central East South America than in neutral years. And over the ZACs, over the South Atlantic Convergence Zone, this is enhanced in both El Nino and La Nina. I think I'll stop here, although there were some interesting results in extreme events. But due to the time, I will stop here.
Thank you very much, Professor Grimm. Sorry for interrupting you, and sorry that you are not able to complete the presentation, but we appreciate your flexibility with the timing. I know this is almost more beyond 2 a.m. and it's really nice of you for sparing your time at this hour. And it also shows your commitment to monsoon research and also the workshop on the monsoon. We appreciate your presentation, and in case there are any questions, probably we can get in touch with you separately. So we will move on to the next presentation. So the next presentation is by Professor Leila Carvalho, also again on the American monsoons. So she is a professor of geography in UCSB, University of California in Santa Barbara, and she actually is one of the co-chairs of the WCRP Climate UX Monsoons panel, and she's closely involved with the International Workshop and also the International Monsoons Project Office. So I now invite Professor Carvalho to begin her presentation. She would like to share her presentation by herself, and I hope this works without any problem.
Okay, do you see my screen? everybody?
Yes, yes. You
Okay.
made it full screen.
Yes. Okay.
Yeah,
You see,
perfect,
okay.
perfect.
Thank you very much for the invitation. I'm honored to be here. I'm Leila Carvalho. And I also would like to thank my team, my collaborator Charles, for his the PI of this project, and all the staff that has been working with us for this project. I will start just showing a little outline. I will give a short overview of the South American monsoon variability. Then I will talk about low-level jets along the Eastern Andes, and then some classification and analysis of those jets, and I will provide some conclusions. But I have to start by talking about the monsoon. What is the monsoon in South America, and what are the main features? And here we see it's just a mean for DJF, mean precipitation, and 50 millibar winds, showing the main features of this South American monsoon. Very clearly, the South Atlantic convergence zone in this region here has this oceanic part and continental part. Here you see the Chaco Low, also very famous. When you look at upper level, then we also see the Bolivian High as part of the monsoon. But what I like to do when I talk about the South American monsoon is to show the monsoon when you remove the mean annual cycle of the winds, because then it looks much more like other monsoons. And what we see here in colors is precipitation. Winds are anomaly after removing the annual cycle. So you clearly see the cross equatorial winds. We see cyclonic anomaly in this region related to convection, and also see the SACZ in this region. We don't actually see much of the Chaco Low because this is there year-round. I want to point out also the importance of this cross-equatorial flow to the southern hemisphere as part of the monsoon. But then the monsoon also has active and break phases. Alice talked a little bit about this. In the active phase of the monsoon, this is precipitation in color. Vectors are showing winds, and I'm showing the actual winds, not anomalies. And then you can see in the active phase, I did this based on an index. I'm not going to discuss this index, but this is basically how the active phase should look like. So you have more precipitation over central and eastern Brazil in this region, and less precipitation over northwest Amazon in this region. Then in the break phase, you see more strong easterly winds. We clearly see more of the anticyclonic rotation in here, less precipitation over eastern Brazil, and more precipitation over northwestern Brazil. So when you take the difference between the two, then we clearly see that you have less suppressed convection over northwestern Brazil, and more precipitation over eastern, and also over where you see the SACZ region, and less precipitation over southeastern South America. All these features are very important, and less precipitation also in the ITCZ, which is very interesting. When you see the difference between active and break phases. So let's talk a lot about the jets and the importance of the jets. So there are a few low-level jets that are very well known in the Americas. We have they are traditionally studied separately. So we have this famous South America low-level jet, which is we see here in this region. This is eastern Bolivia. Then we have the north jet we call Orinoco. Some call Orinoco jet, and then you have Caribbean jet, and then you have the Choco jet. But for this talk, I'm going to focus on these two over South America. And also trying to understand if they are related and how they play a role for the monsoon. But before I talk about that, I need to briefly discuss how we calculate, how we use this or found out about the jets. So we used 4 reanalysis, 5 reanalysis actually. We used the Bonner criteria, which is the criteria that has been proposed for the United States to define about the low-level jets. We modified the Bonner criteria to be adapted to South America, because this criteria is very tuned to the jets that are being studied in the northern hemisphere. So we used similar. We are using winds, wind shear, but we are also using percentiles of the winds. Instead of using thresholds, we use percentile. We use 6 hourly reanalysis, and we look. I'm going to show first by looking at separate regions where we know the jets exist. We know climatologically, we see the high standard deviation in the winds. We are going to look into this 2 regions separately. Okay, so when you have these South American low-level jets, the famous jet over eastern Bolivia in this region, we have maximum winds in this region. Over here, they tend to be nocturnal. They are the type of nocturnal type of a jet. And the importance of this jet is that it transports a lot of moisture from tropical regions to the subtropic. Here, what I'm showing, just to emphasize, is the anomaly relative to climatology when you have the jet very strong in this region. So you can clearly see that when we have this low-level jet strong, moisture is transported to the subtropics and away from the monsoon, and you see more of the anticyclonic circulation. This is low level, and then the easterlies, and then the relationship with suppressed convection in this region. Now we are looking at the northern Orinoco low-level jet, again during DJF. So this is the region where we observe the jet. And then we see this is a composite for the cases, the days when we have those jets. And you can see this is precipitation and winds. And it's very clear where the precipitation is more enhanced. We see enhanced precipitation along the Andes region, in this region, and also along the continental part of the SACZ. When you contrast these observations with the climatology, again, we see more precipitation actually over the monsoon region, and a suppressed precipitation where we see the jets strong. And the reason for that is that, well, you have stronger jets, you have a divergence of the winds, divergence of moisture fluxes. So you would expect to see less precipitation. And this moisture is transported by these anomalous westerly winds along the region of the monsoon. So this is why this jet is important to be well understood. Now I'm showing, this is published in this paper. This is a composite also of this northern jet, focusing more on the northern jet, showing winds anomalies, SST, and here we are looking at upper levels. We are looking at upper levels because it is clearly showing the wave train. Alice showed very well. There is often related wave train propagating over South America when we have convection along the SACZ. And we do see this happening. So there is, even though we have the jet in this region, we clearly see the importance of having both hemisphere perturbing circulation in both hemispheres. This is upper levels. When you look at low levels, we see that a very clear anticyclonic circulation. This is the North Atlantic anticyclone becomes stronger. And this is also important in transporting moisture across the equator towards South America. In low level, you also see the cyclonic circulation, anticyclonic circulation. So the existence of this jet is a combination of interhemispherical dynamics leading to the increase of the jet that ends up affecting the monsoon. But most also important is that this jet seems to be increasing, intensifying over time. We see that they have been increasing in frequency over Venezuela, Colombia, and also in wind speed. As you can see in both cases here, those trends are statistically significant, which is also important in understanding the variability of the monsoon in recent years. Now, if you look at what is the seasonal cycle of those jets, you see that for the Northern Andes is actually peaks in March, but also in the pre-monsoon season, which is very important. Whereas the jet, central jet, it peaks in the winter. But we have also sometimes you have both jets simultaneously. And you know that you have seen, as I showed before, they act in different ways, right? Almost opposite ways, but often they appear simultaneously. So we are interested in understanding what kind of circulation and when do they happen simultaneously? When do they happen independently? So the way we answered this question was by not being so subjective in defining what the jets are, but allowing more of this variability to be recognized by the methodology. So what we did, we look into the reanalysis, again, winds, and then we define a mask along Eastern Andes, all this region for using all these regions. And then we identify for every grid point when the criteria for a jet was occurring. So we use the same criteria before that we used for some points, but now for all these grid points along the Andes, just to find out about what kind of regimes we find. And then we get about 1,700 maps that pass this criteria. And then we used self-organizing maps, SOM, to recognize those patterns. This was an unsupervised neural network tool that used this geospatial data. So here's the data. You have the input data. There are some weights that is being applied. And then the methodology, the method finds maps or nodes that then we will recognize based on weights and as being different patterns. So this methodology, I'm not going to go through this. If you have more questions, I'll be happy to answer. But it end up giving this methodology actually gives 208 nodes, which is a lot. We're not interested in all those possible nodes. So the way we do in order to separate what matters to us, we then go through a Kme clustering method to capture the most important modes. In this particular method, we end up having some supervision, right? We have to decide how many clusters are important. And then we came up with this after several tests with what we thought was ideal. So we have this 10 clusters, and you can see that some of these clusters indicate that you have, say in this case, more of the northern type of jet that becomes stronger in these four first clusters. Then you have some of that show that they actually occur simultaneously. When you see the color, pink colors indicate strong southerly winds, northerly winds, sorry. And then you see that in some of these clusters, they occur together. And then you see these last three ones are showing when you have this Eastern Central Andes jet stronger, right? So you can use this now to try to understand some of these mechanisms. I'm going to shortly show you the northern jet by itself, right? The simultaneous and the central jet. And what is interesting, I'm showing lag composites So leading 2 days, leading 1 day, and during the jet. And you can clearly see how as the jet becomes stronger, a very clear relationship with the westerly winds and the intensification of the monsoon. Whereas you see more of the suppression, you see this cyclonic, anomalous cyclonic circulation forming here. This is low level, right? And enhancing convection over here along the SACZ, where you see the convergence zone. And then if you see when they are the simultaneous, well, they are competing, effects are competing. So we don't see much of this effect. And actually the central end is seems to be more important in enhancing precipitation a little bit in this region. Of course, when you have the central Andes and not the northern Andes, then you have a lot more of this suppression here and moisture transport to southeastern South America and causing extreme events in this region. So in conclusion, this South American monsoon is strongly influenced by the behavior of the low-level jets. This research points out that the north and central low-level jet play a distinct role in modulating the monsoon. The northern jet is more important for the active phase of the monsoon. There is also evidence that the frequency and intensity of the northern jet is increasing, which is important. And the SOM is a useful tool to be less arbitrary in identifying the jet and their behavior. And they can be useful to characterize mechanisms associated with the active and break phases of the monsoon. So thank you very much for your attention. And I stop sharing.
Yeah, thank you very much, Leila, for that very interesting presentation and your innovative ways to make diagnostics of the low-level jet. I think this is of interest, I think almost for all even the other regional monsoons. So if there are any questions, I think we can take one question if someone has a question. Can you raise your hand if you have a question? Okay, I see no request for floor. So thank you, Leila, for that excellent presentation. And we appreciate you also for staying late in the night.
Yeah, I'm taking my coffee. So
Thank you.
Thank you.
So the next speaker is, of course, very well-known monsoon expert, internationally celebrated in the monsoon community, Professor B.N. Goswami. He needs no introduction to the monsoon community. He actually has led many programs in the Indian Institute of Science and also more notably in the Indian Institute of Tropical Meteorology. So the next presentation is about the teleconnection between North Atlantic SST and the Indian monsoon variability, which is actually a new way of looking at the Indian monsoon variability teleconnections. Professor Goswami, the floor is yours.
Thank you, Dr. Rup Kumar. Thank you very much. Can I try to share my screen? If it works, then I'll work with my sharing. If it doesn't, I'll quickly go back there. Okay, let me try to share the screen.
Okay, you can share.
Okay. Is it visible?
Yes, sir, it is visible.
Okay. So, okay, great. Then I'll make it full screen. Is it okay?
It's okay, sir.
Okay. Thank you very much. Okay, thank you very much for giving me this opportunity to talk about this topic. So why am I talking about this teleconnection between North Atlantic and Indian monsoon rainfall? So basically, my talk is about this Indian regional monsoon, Indian monsoon. But in the context of Indian monsoon, I think the drivers of Indian monsoon has been a big question for a long time, and we have known that El Nino is a major driver for Indian monsoon variability. But over the years, we have also known that there are association about Indian monsoon with AMO, There is also with IOD, PDO, and NAO. But none of these associations have been the robustness of these associations are not very well established, and whether they are really drivers of monsoon and independent of El Nino has not been established properly. So over so many years, even the causality or the direction of drivers, even in the case of El Nino, we are not sure, because it is possible that Indian monsoon can also affect the El Nino, while El Nino can influence the monsoon. So which direction does it work has not been established even today very well. So one of our concern has been to establish the drivers, and in that connection, the causality has been a major concern over the years. So which is what are the drivers which have a direct causal association with monsoon? And in that connection, we have done some recent works where we have established this causality amongst several of these drivers. And this is the theme of my talk. And I'll come back to this picture here at a later time. So, so basically, why we are talking about the connection between the North Atlantic and Indian monsoon? In the context of this is that in the as we know, the Indian monsoon is a very complex system. It has several different variability, from biennial oscillations to multi-decadal oscillations. Association with El Nino is quite well known. And it is also known from predictability studies that Chang and Shukla and worked, it is considered to be a highly predictable system. And its potential predictability, potential scale has been estimated to be about 0.85. Unfortunately, however, all actual scale of all prediction systems today is less than 0.7, and that is what we have been able to achieve after monsoon vision, but it has always remained below potential scale. So that has been a major question why, and that is essentially, I believe that there are two reasons for that. One is, of course, the models have their own biases, and the prediction models need to improve bias, and that is happening steadily. And however, more than that, we have not been able to identify all the potential drivers of monsoon clearly and include their contributions into the prediction system properly. And that, I think, is major concern. And in that context, my talk today is in that context, I am going to sort of identify the association with the North Atlantic monsoon as one of the most important potential drivers. And that is the importance of this is that over the last 100 years, Sir Gilbert Walker discovered the sudden oscillation and association with Indian monsoon, and that has of course led to the connection with the El Nino and sudden oscillation. So over the last 100 years, therefore, ENSO has remained a single most important driver of the Indian monsoon, and for its variability and predictability. Unfortunately, the association between monsoon and ENSO has been epochal, has been varying, and over the recent years, in fact, it is very, very small, very low, very poor correlation. And even when it was in the best of times, their association explains only about 35% of the variability of monsoon. So therefore, a lot of variability is not explained by monsoon. Where does they come from? We must identify them. And that is the need to identify non-ENSO drivers of monsoon and incorporate them into the prediction system. That is why this connection with AMO is important. But what have been the problems? So therefore, we need to go beyond TOGA or beyond ENSO and TOGA. So we have to look beyond tropical SST, or maybe even extratropical SST possibly could influence monsoon, but we have not paid enough attention to this. There has been, of course, has been indications that North Atlantic temperatures influence the monsoon in centennial and longer time scales, because mega droughts of Indian monsoon have been associated with cooling in the North Atlantic. And over the last 15 years or so, we have investigated this association between monsoon in North Atlantic SST and Indian monsoon on interannual and multi-decadal time scales. And we find that that is quite a robust association. But there are some issues that we needed to clarify, and that is what my talk today is on those issues. Teleconnection. And one of the issues, of course, was to establish what is the physical mechanism by which the North Atlantic SST could possibly influence monsoon. And so that teleconnection mechanism has, over the years, last decade or so, has become much more clearer. I'm going to give an example of that. But there are some few major conceptual concerns because the concern was that the tropical SST influence teleconnection has to happen through this circulation, right? So it is a kind of atmospheric breeze. Atmospheric breeze has to happen through the circulation. But how does the North Atlantic SST, which is a pretty extratropical SST, which is pretty mean SST is very cold, how does those cold SST or variations of those cold SST could influence the circulation, which then influence the teleconnection? And that has been a major conceptual problem because unlike tropics, the variations in the mean sea surface temperature over extratropical region or the North Atlantic is much lower, and at that time, even the small change, even a large change in SST does not change the evaporation so much, and therefore cannot influence the convection like it does over the tropics. Therefore, there is a question about that. In fact, people general thinking has been that. That it is not the SST that influences the circulation in extratropic, but the circulation affects the SST through fluxes in the extratropic. This has been a connection. Therefore, there has been always a conceptual problem of how SST could have influenced this. In the next few slides, I'm going to show that, in fact, SST can influence the extratropical circulation, not on synoptic time scale, but on the slower time scale, like supersynoptic or the intra-seasonal time scale or seasonal time scale. In fact, in that time scale, SST indeed can influence the circulation, and it can influence vorticity and circulation, and that can produce a certain forcing in the atmosphere. And that forcing then, therefore, not simply just the SST convective forcing, but by changing the circulation itself, it can produce vorticity forcing. That vorticity forcing can introduce, again, circulation anomalies that can produce atmospheric breeze. Some time back, we had actually identified that on multi-decadal time scale, the North Atlantic SST and Indian monsoon rainfall are pretty well correlated. And so, therefore, in addition to the centennial time scale, there is a relationship between the North Atlantic SST and Indian monsoon rainfall on multi-decadal time scale. Now, even on interannual time scale, that there is a relationship, and that relationship has been recently studied by one example of such relationship is the study by Bura et al., where they looked at all non-ENSO drought years of Indian monsoon, and when you do composite of all the sea surface temperature anomalies of non-El Nino drought years and El Nino drought years, these are El Nino drought years and non-El Nino drought years. El Nino drought is, of course, El Nino signal is very strong. North Atlantic SST is very weak, but on non-El Nino drought years, the North Atlantic has a very strong cooling, very significant cooling, and there is no SST signal in the tropics. There is no El Nino signal. Nowhere there is a major signal. So the tropics is in the transition from between El Nino and La Nina, and there is no signal, and only signal that is there of SST is in the extratropics. So there is clear indication that SST in the extratropics may have influenced the drought years in the monsoon. And how did they do that? So they looked at found out that if you do composite of these, unseasonal mean time scales of the wind anomalies associated with these events, you find that there is a strong teleconnection through a wave train, a stationary wave train, which goes all around the world, including coming over India. And this is a barotropic wave train, which is sitting on the top of this SST. It starts over the North Atlantic and then produces a stationary structure around the globe. And that influences the circulation over Indian region. And that circulation then affects the rainfall, modulates the rainfall over monsoon region. So therefore, the teleconnection is wave train, which has been initiated by a barotropic vorticity over the North Atlantic, and this barotropic vorticity happens on intra-seasonal time scale. They are episodic. They last for about 3 weeks, and then die, and then again produce another one event. And in the season, if there are 2 events, it really produces a major structure like this, and that is essentially what influences monsoon. So we have found that exactly the same Rossby wave train also influence on the multi-decadal time scale. So we did a sort of regression of this SST multi-decadal component of monsoon on the winds and geopotential height, and it shows exactly the same kind of Rossby wave, stationary Rossby wave, which influence, and that part is amplified here in this region. So this same kind of Rossby waves which affects the circulation over our region, and that influences the monsoon. This is quite different from the ENSO kind of teleconnection on an interannual time scale, where the wave train is in the meridional direction, propagation direction is sort of meridional, but here this is kind of a zonal waves itself, but there is an extension of that wave towards subtropics, which influences our region. So this is the difference between, and this is now sort of it's pretty well documented now. So that is clear, but the question is, now how does that actually affect the monsoon rainfall? It turns out that these, as I said, these Rossby waves or the barotropic vorticity over that SST region is episodic of intra-seasonal time scale, and that intra-seasonal time scale it sets up this stationary wave, modulates the stationary waves on the intra-seasonal time scale, and that intra-seasonal modulation essentially modulates the intra-seasonal activity over the monsoon region, and it sort of what you call phase locks these monsoon active and break spells, long active and break spells are phase locked with the seasonal cycle, and that phase locking, in the case of positive AMO, give rise to positive active spells, and they are very much associated with the vorticity. Indeed, this is the vorticity activity in the North Atlantic, barotropic vorticity. So this barotropic vorticity seems to drive these active spells. And same thing happens in the opposite thing happens in the AMO negative phase. So this is based on about 20 years of data on intra-seasonal time scale. They always seem to, every time when there is a positive thing, they tend to phase lock the active spells during a part of the seasonal cycle, and therefore, even when we do composite, the active spells seem to be are there, or break spells are there. So therefore, the circulation modulates in such a way to phase lock the long active or break spells and thereby affect the seasonal mean. So therefore, the mechanism is essentially happens through intra-seasonal time scale. The sum together of these intra-seasonal activity gives rise to, even on this on the stationary wave, the intra-seasonal time scale, the stationary structure is same as the seasonal structure, because the sum of these give rise to that, and some of the seasonal structure is same as the as the multi-decadal structure, because sum together of that seasonal structure actually results in the multi-decadal structure. So therefore, it's the same mechanism which affects from the intra-seasonal time scale all the way to the multi-decadal time scale. So that is the mechanism that we know. But still, there is one big question about how the vorticity, how the barotropic vorticity is produced by the SST. Do the SST really drive the barotropic vorticity? So that question was not very clear. So what to do that, we did certain lead lag analysis of SST and barotropic vorticity in over this all the grid points in the northern hemisphere, and we did for that we removed the synoptic variability by doing weekly data rather than daily data, or filtering it, just weekly data. And if you do that and do a lead lag relationship, it turns out that the maximum correlation happens one week after the SST. So SST leads the vorticity, and of course there is a negative correlation, but that it happens over in North Atlantic as well as over North Pacific. These two things are both are part of the same system. AMO is associated with positive anomaly here, also positive anomaly here in this region. So, or negative anomaly here or negative anomaly there in this region. So therefore, these two are connected, and this indicates that SST could do this. But still, this is still the linear correlation analysis. So still, the cause and effect was not very clear. Now, cause and effect, it is not clear because these are basically linear. But most of the functional relationships are non-linear because the time scales are different, right? So one is on internal time scale, one is on multi-decadal time scale, and then some intra-seasonal to multi-decadal, there are different time scales. So therefore, the relationships are actually non-linear. So how do we establish that? So and also the conditional independence of these drivers have not been established. So therefore, what we did is we decided to calculate the causal connection between ISMR and ENSO as well as in the presence of the other drivers. So what this can be done today with different techniques are available. Granger causality, and this has been used in AI and ML field a lot. But here there is another one, something called PCMCI method, which is also very popular today, and there is, I cannot go into details of that, but we use this PCMCI plus method, which calculated a sort of this methodology involves this lead lag relationship or the lead lag regression, but also it uses the nonlinear dependence between them. So, and then uses a large number of ensemble to find probability of which direction connection, which lead lag is correct, and which lead lag has a higher probability, and then establishes a statistical significant association, directional association with the driver. So what we did is that we looked at all these at 5 different potential or 6 different potential drivers, and use this PCMCI method to find all the possible connections between them and see which one is actually driving which one. So with that leads to something very, very interesting, and we find that, so this, what it means is that, so this, whenever there is this no directionality, so that means that there is a simultaneous lead lag relationship. So the straight lines are simultaneous relationship, but this the curved lines means there are lag relationships. So that means this is positive, and the color represents positive or negative correlation. So this is a positive correlation with a lag of positive connection with a lag of 3 months. So IOD it can drive ENSO with a lag of 3 months. On the other hand, ENSO has a direct connection with a simultaneous connection, which we know. ENSO has a negative connection with IM. But ISMR can also influence the ENSO with a lag of 1 month. Okay, but most interesting thing that we find is that, so when there is no directionality, that means the method cannot find out from the data, we cannot really have a clear idea of who is affecting whom. This is called confounded relationship. So, therefore, the simultaneous connection between IOD and NINO is not clear, which one is affecting whom. But IOD seem to have an influence on NINO. On the other hand, I think the most clear signal that has come out is also that AMO is a definite driver of ISMR with a lag of about 3 months. Okay. In Atlantic NINO, we have found associations ISMR, but we cannot find a clear directionality in that connection. IOD also has an association with monsoon, and people say that IOD can drive, but unfortunately, that connection is not very clear. And we have done with different data sets and looked at, and there is a potential, and some data set do show that there is a weak connection between IOD driving ISMR, but with small changes in the data set and all that, this does not appear again. So therefore, this seems that there is a possibility of IOD influencing ISMR, but it is a weak connection. The connections sometimes are not very stable. So I think one thing that comes out very clearly is that both AMO and NINO are two drivers of ISMR, but the other drivers are not very clear, and they may not be independent of El Nino. But AMO appears to be independent of El Nino, and still a driver. So I think this is a new understanding that has emerged from this analysis. So going a little deeper, how does this mechanism of how does it work on the intra-seasonal time scale? Do the North Atlantic SST produce the barotropic vorticity over there? And do that barotropic vorticity affect the upper level vorticity over the over the Indian region? And that upper level vorticity, does it affect is connected to the lower level vorticity and rainfall over region? So to do that, we had used this North Atlantic. It is on intra-seasonal time scale. So these are data which is filtered on intra-seasonal 5-day running mean averages of data, and use that data on intra-seasonal time scale, and use the long data of that, and do all these statistical calculations, probabilities of connection. It turns out something very robust connection comes out, as North Atlantic SSTs indeed drives these, which is consistent with our correlation, the barotropic vorticity over that region, and North Atlantic SST has a direct connection with ISMR intra-seasonal variability, but that connection happens through these barotropic vorticity affecting the upper level vorticity over the North Indian region. That upper level vorticity is strongly linked to the lower level vorticity that modulates the lower level vorticity, and lower level vorticity, of course, is related to our rainfall. So it is not. So one possibility, some argument, reverse argument can be that okay, if monsoon is fluctuating on intra-seasonal time scale, obviously that will have a lower level vorticity connection associated with this, and that lower level vorticity will have a divergence, upper level vorticity will be associated with it. But this data shows clearly that it is the modulation of this upper level vorticity is affecting lower level vorticity, not the other way around. Or not, the ISMR is not affecting the lower level vorticity. It is the lower level vorticity that is affecting the ISMR. So this is clearly shows that external forcing are. Okay, I am done, almost done, I'm done. Okay, so with that, I think new knowledge has been, I think, established. I think this is something important, but I'll just conclude with the future direction. I was almost to the end. So basically, I think it is important that the establishment of this the connection with the North Atlantic is now, I think, pretty well settled in the sense that, so therefore we must try to include that the North Atlantic forcing in the prediction models. In other words, models must be able to capture those variability in the North Atlantic to improve the ISMR prediction. And in addition to that, I think we need to do, in terms of prediction, we need to look at potential scale at long lead prediction, because these indicate that there should be long lead predictability. But today there is no estimate of long lead predictability. And what is the prediction scale after 12 months or 24 months? We really don't have a handle on that. So recently we did some work on that, and we estimated that actually the monsoon, Indian monsoon, has a pretty high predictability even at 18 to 24 months. And this is something that is work I am not presenting here, but it is work that is under review. So I think with that I'll stop, and if there is time I would be happy to answer any question. Thank you very much.
Thank you very much, Professor Goswami, for that very inspiring and exciting lecture. And it is, in fact, great that you have actually opened new doors to attack the unmet potential of the potential predictability of the monsoon. I think it is quite optimistic. So I think we are already quite delayed, but if there is any question, I think we can take one question if anyone wants to take the floor. Okay, I see no request for the floor. So once again, thank you very much, Professor Goswami.
Okay,
So
thank you so much. Thank you. Thank you.
Yeah,
Thank you. I will stop sharing. Okay.
Okay, we'll move on to the last but not the least item of today's session. The next presentation is by Dr. Sanjay Srivastav, who is the Chief of Disaster Risk Reduction Program at the UN Economic and Social Commission for Asia and the Pacific, generally known as UNESCAP. So he has been closely associated with the South Asian Climate Outlook Forum, and we have been closely working with him. So he will come back to us with the impact-based forecasting angle of monsoon prediction. So he will tell us how the monsoon outlook can be taken to impact forecasting scenario. Dr. Srivastava, the floor is yours.
Yeah. Thank you, Dr. Rupakumarji. Thank you very much for this opportunity. And let me try if I could able to share from my side. Otherwise, I will request my colleague to manage from your side. So I think there is some problem. So you can share from your side, Dr. Radwan. Yeah, you can share the slide. Yes. This is it's a honor and privilege to talk to some of the domain expert of the monsoon, and I'm just taking you to some different tracks. Different track in the sense that, you know, in WMO there is a paradigm that what weather will be to what weather will do. So similarly, if you take that paradigm in case of Asian monsoon, what monsoon will be to what monsoon will do, how it will impact economy, how it will impact the most vulnerable. So there's that story, the narrative which I'm going to share with you is from a professional of United Nations Regional Economic Commission. So it will give you some economic sense of monsoon, particularly the understanding of the monsoon and the monsoon predictions. So this is a narrative on the impact and policy based on the monsoon seasonal forecast of the monsoon. So my next slide is going to tell you the before you make any forecast, my colleague Dr. Mohapatra has dealt at length. You need to have a understanding of the risk and impact a priori. The understanding of risk escape, that's the landscape of risk in Asia Pacific. If you convert this in terms of the money, monetize the risk, what is going to be seen is the Asia Pacific region loses $675 billion per year. This is annualized average loss. Out of this is the 2.4% of Asia Pacific gross domestic product, GDP. This is the growth engine of the world. And 2.4% losses is quite substantial, not sustainable. It's not good for achieving sustainable development goals in days to come. But when you do a diagnostic analysis where these losses are coming from, we did this analysis and we found that 85% of this 675 billion losses are coming from the climate-related disaster, climate-related hazards, out of which, surprisingly, 60% comes from drought alone, which is direct, indirect losses of drought across the multiple sectors which impact the drought. So 60% drought, 13% tropical cyclone, 13% floods, and only 13 to 14% earthquake and tsunami. So if you see the risk escape in the region, how the Asia Pacific region is losing in terms of the money, it's 85% comes from climate-related disasters, that is drought, tropical cyclone, and floods. If I come to my next slides, our next analysis shows why monsoon is so important. Because basically the monsoon is a risk driver. And when you see the 85% of the climate risk of Asia Pacific, this is over the time, it is from June to October. This is the month where there are largest losses coming from the climate risk profile. And that is the time of the monsoon, Asian monsoon. So most of the seasonal forecast that captures this Asian monsoon temporal profile. So you see, for example, the probability of the risk of the floods, which peaks from August to September down the line to the October. Whereas in case of the drought, you see the other. So what happens is, if you convert this seasonal forecast, the time domain, to the impact forecast, so overlay seasonal forecast to the exposure of the economy, people, the vulnerable context, you can simulate what could be the impact of monsoon this year in Asia and Pacific. So my next slide is going to tell you the impact story. This is a methodology that we developed. This is a WMO Climate Services. I'm happy Dr. Kumar Kolli is here. He has been the champion of the framework of the climate services, which I think now in a operationalized in many ways, and also in Asia Pacific region. So we have operationalized this. We have used this hazard information from the monsoon forecast, especially the seasonal forecast, hazard information in terms of all climate related risk. Then we have intersected this in terms of the exposure to the population and some of the critical sector, which is in the framework of climate services like agriculture, energy, health, and disaster management. And then brought it down to identify the people who are most at risk hotspots, and the potential impact on the economy. So this is the impact-based forecasting framework, which we are following it up with WMO in many countries. So my next slide is going to tell you that if you click the bottom, this is the WMO Seasonal Outlook of 2021, June, July, August. So this seasonal outlook, how we convert in form of the impact outlook. So if you click the next one, yes, you see before you translate this seasonal outlook, you have to see your hot spot of drought and flood in Asia Pacific regions. So left-hand side, it indicates the hot spot of drought, floods, and also the vegetation condition during the period when you are making the forecast. And then you look at all three in conjunction, overlay over each other. So whether in a hot spot of the floods, where there going to be a deficit rainfall, or hot spot of drought, there is going to be a surplus rainfall, which gives you a clue how could be a impact outlook in times to come, particularly for flood and drought. The next slide is to show you, yes, the next slide is when you intersect this monsoon, Asian monsoon forecast. What is very clearly, we have used the gridded world pop data. It's a very standard gridded information which UN DESA has produced. The population worldwide is in digital form. And then when you intersect seasonal forecast, you see 40 to 60 below normal rainfall. There are 670 million people, and where those people are located, it is indicated in the circle. When 60 plus above 78 million people, where they are located is indicated. And same, those who are above, below normal. So people who are likely to be affected by floods and drought is indicated. So this gives you a clue, a early warning for the early action. The people who are likely to be impacted by this monsoon floods or drought, where they are, what could be the possible risk hotspot. The next slide is to show you the most vulnerable. This is the thanks to our UNDP. They have developed a gridded database for HDI, Human Development Index, and you use the most vulnerable people. Nowadays, we call it multi-dimensional poverty, where the most vulnerable people are located and how they are going to be impacted by floods and drought during this monsoon season. So you locate, you identify, it is spotlighted, the most vulnerable, which will have which is going to experience drought in the season or flood in the season. So you narrow it down, identify the hotspot. The next slide is to show to you some of the energy sources, the power plant, hydroelectric power plant. Before coming to this, you must know hydropower in certain country context is key for energy security. For example, in Myanmar, 56% of the energy comes from hydropower. Same as Vietnam, Cambodia. So in Nepal, it is more than 90%. So if you take the contribution of the energy in a particular country's power sector, it's very important to develop the impact forecasting. So my next slide is going to show to you the agriculture, which is, of course, monsoon drives the agriculture systems, but especially in the Asia. So when you see which part of the season, there is a likely impact of the flood and drought on the agriculture system. And then you look at agriculture from its critical role in the economy of a respective country. For example, in India, it's like a rice export. The global value chain, India contributes 33%. Same, Thailand contributes 19%, Vietnam 12%. So the lack of flood or drought during the monsoon period is going to impact the global supply chain of the food system. And that's very important information for the policy, the impact and policy dynamics. The next slide is going to tell you how this information is disseminated for. This information is to come to from a research to the analysis to the public policy arena. We used many of the existing platform. Dr. Rup Kumar is aware of some of this. The regional climate outlook forums, we used convert the seasonal forecast to the impact outlook, disseminate it to regional climate outlook forum. There are many regional climate outlook forums in Asia and Pacific region. In many countries, UNSCAF has funded monsoon forums. And through RIMES, we reach down the line at the monsoon forum and then develop the adaptation tool. So it's a outlook to impact, to preparedness plan, and to monitoring. This is how you can manage the risk of the monsoon system, monsoon season in times to come. My next slide is going to tell you some very specific what we did in South Asia Climate Outlook Forum. So this is a SASCOP, South Asia Climate Outlook Forum, and this was converted from a seasonal outlook to impact forecasting. So next slide will tell you some of the impact forecasting product. Of course, I don't want to give a tall claim, but what was surprise for all of us was in 2021, when we used the seasonal forecast SASCOF data, 3 months, I think it was sometime in month of April. And then we brought this impact forecast, and then some of the forecast, for example, in August, September, Pakistan was severely hit by heavy rains and experienced urban floodings, 400 lives lost. It was indicated very well in advance. So many of the hot spots, which were indicated very well in advance, were found happen in due course of the time. So a probabilistic forecast has its own limitations. All of you are aware of it, but it gives you some kind of a directional, what we call in the language of the early warning system, early warning to early action. So it narrows down your target area of the response. And that's where the monsoon forecast impact makes a lot of sense in terms of impact and policies. The next slide is to tell you that to operationalize the climate services, and particularly the monsoon impact forecasting, we have developed a risk and resilience portal. All the data that I shared with you, because it's an era of digitalization, included the gridded world pop data, all infrastructure layer. UNSCAP is a custodian of all energy, the transport, all infrastructure layers. So all the digital databases are here. So you can make use of it. What Dr. Mohapatra, my friends, told. These are the digital data. It can be used for impact forecasting at a broad level, not micro, but macro level in Asian regions. So I think this was my last slide. And thank you once again for giving this opportunity. It's important to take science into the policy domain, and this is an effort to take it to the policy domain. So thank you, Dr. Rupa. Thank you very much.
Thank you, Dr. Srivastava, for that very encouraging presentation. And in fact, what some of your statements are music to my ears, because we always have this kind of concern that seasonally aggregated information may not be of much use in decision making, but you have clearly demonstrated how even seasonally aggregated outlooks can be taken forward and actually converted into impact-specific decisions. That is really very encouraging, and I hope you will continue your support to the Climate Outlook forums and help us understand the user needs and try to improve the way we generate our forecast and make them more reliable and more detailed in terms of space-time resolutions. So before we close the session, if there are any questions to Dr. Srivastav, I think maybe we can take one question. Ashrit, you want to ask something?
Yeah, thank you. That was a nice talk, Dr. Srivastav. I just was wondering with one of the graphic, which was very interesting, which indicated that floods seem to have very swift impact, and there is only time to respond. There is actually no time to prepare. While the impact of droughts seem to be like they build over a time. So that gives an impression that there is possibility, there is scope for preparation through early warning and impact-based forecasting, things like that. How can we prepare and make use of the forecast for preparing for the drought, if you have some vision on that? Thank you.
Thank you, Dr. Raghavendra. There are excellent. I think NCMRF is one of the frontiers in this area. What our perspective, particularly from the UN side, was unless you convert your forecast into the impact, you heard Dr. Mohapatra's, but in India context. I'm talking about Asia Pacific region. We bring out World Bank, ADB, UNSCAP, economic outlook. So in economic outlook, we are using the ARCOF data, the seasonal Dr. Rup Kumar, what she was highlighting. Suppose if this monsoon season in South Asia, where there are agrarian economies and more than 20% of the GDPs of South Asia depends on agriculture. If there are shortfall in, let us say, if there are more likely floods or drought, to what extent it is going to impact the economy. So we bring out a kind of a economic outlook, and we are integrating nowadays SASCOP into our economic outlook. So in a country, for example, if I am talking from UN perspective, a country which has to take decision on the import or export of the food grains, there are countries who are likely to be deficit, and those are all the poor countries. So what could be the trade regime? What could be liberalization of the trade to support the most vulnerable in the country? So those are the policy area. And in case of drought, suppose I must share with you some of the examples. In Vietnam, there was a foresightedness, there was a outlook about a drought, and the country could able to prepare well in advance. Like you rightly said, for flood and tropical cyclone response time is very limited. For drought response time is substantially is considerable in terms of preparing the country and response agency. So this is happening. That is where you need impact-based forecasting and target those people who are likely to be impacted by drought. That's the reason I specifically pinned down Human Development Index, HDI, the gridded data, and you just pin down, these are the people who will be impacted by the drought. So all your drought-related interventions to protect the vulnerable and poor should be risk-informed, and it should be known well in advance. Right.
Thank you. I think that is a good point to end this very, very interesting session. In fact, this actually sets the scene for the entire workshop. We had 6 really high quality presentations from eminent personalities. I think we had a lot of information on the regional monsoons and also the impact aspects. So this is a great beginning for the international workshop on the monsoons. And once again, I thank all the speakers for their presentations, and also some of our colleagues from the Americas for staying up very late in the night and making their presentation. This is very encouraging. So, and with that, I also thank the International Scientific Committee for giving me this opportunity of chairing this session. And now I give the floor to the organizers for their housekeeping announcements.
Thank you very much, sir, actually, for nicely chairing the session. And this is a good beginning, actually. In the morning, our local morning, in fact, we are thinking how this part day will proceed. So everything went well. So I think it was a very good beginning. And tomorrow we'll have a formal inauguration also, where the Secretary General recorded message is there. Our secretary will be there, and there are many eminent people are there. And then also there are some function like IMS will provide the president, the Gilbert Walker. All these things are pending tomorrow, and also many scientific sessions are there lined up. So I think with that we'll close this first day of the session. And thank you to you as well as all the speakers and the panelists who that like Professor C.P. Chang and Dr. Ajit Tyagi sir, Mohapatra sir also gave the formal welcome address. So thank you very much, sir. With this, we will just closing our first day of the. You can just visit our website for any further update or anything that is for tomorrow onwards. Thank you very much. Namaskar.